Students, there is a problem up on your screen, a picture of two graphs, and a question asking what is the solution to this system of equations. It probably won't take you very long to look at the graph and identify the solution. Our solution is right here where the two graphs intersect. So the solution will be the point 2, -1. But now I want to think about why that is the answer. This green line here, going this direction, is a set of solutions. Every single point along this green line is a solution to the equation that represents this green line. Every single point along the red line is a solution that represents the equation for the red line. So if we want to find the solution to a system of equations, we're looking for the one point that is a solution to both things. And since these are all the green solutions, and these are all the red solutions, the only solution that's a solution to both lines is this intersection point right here. Today we're going to be talking about something slightly different, but it's very similar and very related to the example we just did. So the problem we just did was review. It was a review of systems of equations. But now we're going to be talking about systems of inequalities. Now, equations have equal signs, but inequalities have less than or equal to signs, greater than signs, things like that. So we're going to be talking about systems, which are two or more, but systems of inequalities, which would be two or more linear inequalities. So the definition of a system of inequalities is two or more linear inequalities that are graphed together, so on the same graph. The solution to a system of inequalities is going to be the overlapping region of points that satisfies both inequalities. Now that's very similar to the solution to a systems of equations, where we're looking for the point that's a solution to both equations. Now we're looking for the points that are solutions to both inequalities. So let's talk about the steps to finding these solutions. We're going to start out with two equations in each of these problems, sometimes more, but most of the examples we'll do together will have two equations. We usually want to start by putting the equations in slope-intercept form. That's y equals mx plus b, but we won't always have an equal sign here. We'll have like a greater than sign or a less than sign, or greater than or equal to, less than or equal to, things like that. So we can have any one of these signs here in our slope-intercept form. Once we have our slope-intercept form, it's really easy to figure out our slope and our intercept. So graphing becomes very easy. You find your m, you find your b, you figure out whether your line is dotted or solid, and that depends on dotted, solid, and then you have to figure out whether you're going to shade above or below your line, and that's above would be greater than, below would be less than. So you're just paying attention to your symbols there. And so far, up to this point, we've done this. That's what we did last week in class, everything above the green line. So we have a new step now. Now we're going to identify the solution. And the solution has to be a solution to both equations. So you're going to have shading from both lines. We need to find the shaded area where both of the graphs overlap. This is going to make a lot more sense once we do a quick example. So let's start with example 1. We want to solve the system of inequalities by graphing and then answer the accompanying question. So let's zoom in to number 1. We're starting with these two equations. Y is greater than x plus 2, and y is less than or equal to negative 2x minus 1. Our first step would be to put these into slope-intercept form, y equals mx plus b, but they actually both already are. So our first equation, we could think of this as a 1x plus 2. Our m is 1 and our b is 2. So let's draw this inequality on our graph. We start with our y-intercept, which is at positive 2, and then we use our slope, which is 1 over 1, to go up 1 and right 1, up 1, right 1. And then we can go down in the other direction as well. So our first inequality will have a boundary line that goes through these points, and since it's a less than sign, we'll have a dotted line. And since our inequality is a greater than, we're going to shade above the line. So I'm not going to do a full shade. I'm just going to do a really light shade to kind of remind me later that we're shading above this line, but we're not sure if that's actually part of our final answer yet. So I'm just going to leave it like this for now. Let's look at the other equation. This one is also already in slope-intercept form, so we can quickly pick out our m and our b and begin drawing it on the graph. So if our b is -1, that's right here, our y-intercept, then we find our next point by using a slope of -2 over 1. That's down 2, right 1. And we can take this up in the other direction as well. And the line, the boundary line this time, is going to be solid because this is a less than or equal to sign. So we can just draw a solid line this way. For shading, notice again, since it's a less than or equal to, we're going to be shading below this line. So below, 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 below. Now our ultimate goal is to find the region, the single region, that satisfies both equations. So I'm going to use a different color here. Let's look at this region over here. This region that kind of goes in this direction, it would be all of this area. This region is not a solution to either equation. Notice we have no green or any blue marks in this region right here. So this is definitely not a region that's in our solution. What about down here? In this region, we've got some blue, but we don't have any green. So this region, from like here to here, that's not part of our solution either. Remember, it has to be a solution to both equations. What about this region up here, from like here to here? This is a solution for the green equation, but not for the blue one. And finally, this region right over here. This is what we want. Remember, we shaded below the blue line, and we shaded above the green line, so this region over here would be shaded by both colors. So this area is our solution. And a few things I want to point out about this region. Anything along a solid line is a solution. So all of the points along this solid blue line are part of our solution set. However, down here we have a dotted line. These points are not part of our solution. What about this one right here, where they intersect? That is a solution because it sits on the blue line. As long as it's part of a solid line, it's part of the solution. So what I drew in red represents our solution set. So we could answer the 3 questions below this simply by looking at the graph now. Is 2, 0 a solution to the system? Well, let's find 2, 0 on the graph. 2, 0 is right here. That is way outside of the region that we've identified as our solution. So no, this is not a solution. The second one says, is 2, -5 a solution? Notice that this sits on the blue line. So 2, -5 is a solution to the blue line, but is it a solution to the system? Another way of saying this is it a solution to both lines or both inequalities? And the answer is no. It's a solution to blue, but it's not a solution to green. The last point is -3, -1. Now this one is the trickiest of all. If it were just slightly above where it is, it would be right in the red region, so of course it would be a solution to our system. But it's not. It's on the dotted line, and points on the dotted line are not solutions to the system. So the answer to all three of these is no. Let's do another example. In example 2, we have a bit more work ahead of us because these two inequalities are not written in the form y = mx plus b. Why? Well, y isn't by itself on the left, so we need to get y by itself on the left. So I'm going to take the first equation, x plus y is greater than 4, and I'm going to move this around by subtracting x from both sides. That'll give us y is greater than -x plus 4. This is now in the form y = mx plus b. So I'm going to fill this in. Let's use green. I'm going to write in a 1 here, so it's easy to see that our m is -1 and our b is +4. Let's draw this inequality on the graph. So b is right here, and a slope of -1 over 1 goes down 1, right 1. And since our inequality symbol is a greater than, and it doesn't have an equal to component, again we have a dotted line. So we'll just draw kind of a dotted line going through these points. And finally, since it's a greater than symbol, when we go to shade, we're going to shade above. So we're shading kind of in this region. Now let's look at our second equation. Our second equation starts out as x plus y is less than -1. And to get that y by itself on the left, we need to subtract x from both sides. So we end up with y is less than -x minus 1. We don't have a number written here, so I'm going to throw a 1 in front of our x, which means our m is -1 and our b is -1. So let's graph this. And once we have some of our points, we can go ahead and draw our boundary line. Now again, our boundary line is going to be dotted. So we'll just do kind of a dashed line all the way through these points that goes on forever in both directions. And since it's a less than symbol, we need to shade below this line. Okay, so this is very interesting. Our graphs, our two inequalities, do not overlap. Those boundary lines are parallel to each other, so they're never going to cross, and those shaded regions are never going to touch each other. So we have a very interesting situation. The first question is -10, -4 a solution to the system? Well, -10 is going to be kind of way off to the left. Let's say it's like all the way over here. -4 would be down about here. So here's -10, -4, which would be in the blue shaded region if we continued this all the way over here. But just because it's a solution to the blue inequality doesn't mean it's a solution to the system. To be a solution to the system, it has to be a solution to both. So the answer here is no. And the point 4, 0 for the next question would be right here. Is this a solution to the system? Well, it's not even a solution to the green inequality because it's on a dotted line, and anything on a dotted line is not a solution. So it's not a solution to green, it's not a solution to blue, it's not a solution to the system. But let's think about this a little bit more deeply. Are there any solutions to the system? This point over here might be a solution for green, but it won't be a solution for blue. Points in here won't be solutions for anything. And points over here might be solutions for blue, but they're not solutions for green. There are no points on this entire graph that would be in both the blue region and the green region. So the answer here is no. There are no solutions to the system. There are solutions to blue and there are solutions to green, but there are no solutions to the system. Let's take what we've just learned and try to apply it to a word problem. So we have a graph that compares calories, which are kind of like our x. We can call this x, and fat, which we'll call y, just based on where they are on our graph. And the question says, Mr. Flowers is on a restricted diet that allows him to have between 1,600 and 2,000 calories per day inclusive. Inclusive just means that he can have 1,600. Sometimes when we say between 16 and 2,000, we actually mean 1601 to 1999, but we mean he can actually have 1,600 or 2,000. So that's what inclusive means. So he has to have between 1,600 and 2,000 calories, and he has to have between 45 and 55 fat. So we want to know what intakes are acceptable for him when we take both calories and fat into account. And we're going to draw it on the graph. So we already said that calories are X and fat is Y. So when we're told that his calories have to be in between 1,600 and 2,000, the way we would write that is 1,600 has to be less than or equal to X, which has to be less than or equal to 2,000. Notice X is right in between 1,600 and 2,000, and it can be equal to those. That's what inclusive means, which is why we have the equal to symbols along with our inequality symbols here. Then for our Y, his fat intake is restricted to between 45 and 55 grams inclusive. So he has to have 45 is less than or equal to Y is less than or equal to 55. And for the same reason, we have equal to symbols here because it's inclusive. And we're using Y because that's just what we decided we were going to represent fat as. So now let's take these two pieces of information and draw them on the graph. This is going to be a little different than some of the examples we've done so far, but let's start with the X's. Our X values have to be in between 1,600 and 2,000. So let's go here. 1,600 would be right about here, and 2,000 is right here. And so we're going to draw a line. It goes straight up and down, here, and here. And this area in between represents the solution to that inequality. It represents all of the X values in between 1,600 and 2,000. Notice how I shaded in between. Another thing I want to point out is I used a solid line. That's because it's inclusive. It's because we have equal signs along with our inequalities. The next inequality says that Y has to be in between 45 and 55. So let's go back to our graph. 45 would be right about here, and 55 is here. So if Y has to be in between these two values, it has to be in between these two lines. So we would shade this area right in between. The solution to the system is the set of all points that satisfies both inequalities. So it would be the shaded region that's both blue and green, or in this case, this area right here. And since it's inclusive, since these are solid and the green lines are solid, then all of these points are included. We don't have to worry about dotted lines or anything. So the red box right there is the solution to our system. So the last part of this question asks us to list 3 possible solutions. Well, every single point in this red box would be a solution to the system. So we could pick any 3 points in there we want. Let's pick this one right here on the corner, something kind of in between, and something right here at the top. The solution down on the bottom right, that looks to me to be calories 2,000 and fat 45. Or we could just write that as 2,000, 45. You can write it as a point, that's fine. One solution, another solution I marked here looks to be at about oh, I don't know, maybe calories 1800, fat 50. So we could write that as 1800, 50. And then the last solution I identified looked to be about calories 1700 and fat 55. So we would write that as a point 1700, 55. So you can pick any 3 points you want as long as they're inside this red box. I just picked 3 random ones that look kind of nice, and I drew what appeared to be a ladybug with little antenna. Ignore me. So this concludes the guided notes for systems of inequalities. Make sure you've copied all these notes down, snap a picture of your work, and submit it on Canvas for credit for following along with today's video and doing your guided notes. Good luck!